Hydrogen is a chemical element with symbol H and atomic number 1. With a standard atomic weight of 1.008, hydrogen is the lightest element on the periodic table. Its monatomic form, H, is the most abundant chemical substance in the universe, constituting roughly 75% of all baryonic mass. Non-remnant stars are mainly composed of hydrogen in the plasma state. The most common isotope of hydrogen, termed protium, name rarely used, symbol 1H, has 1 proton and no neutrons. The universal emergence of atomic hydrogen first occurred during the recombination epoch. At standard temperature and pressure, hydrogen is a colorless, odorless, tasteless, non-toxic, non-metallic, highly combustible diatomic gas with the molecular formula H2. Since hydrogen readily forms covalent compounds with most nonmetallic elements, most of the hydrogen on Earth exists in molecular forms such as water or organic compounds. Hydrogen plays a particularly important role in acid-base reactions because most acid-base reactions involve the exchange of protons between soluble molecules. In ionic compounds, hydrogen can take the form of a negative charge, i.e., anion, when it is known as a hydride, or as a positively charged, i.e., cation, species denoted by the symbol H+. The hydrogen cation is written as though composed of a bare proton, but in reality, hydrogen cations in ionic compounds are always more complex. As the only neutral atom for which the Schrödinger equation can be solved analytically, study of the energetics and bonding of the hydrogen atom has played a key role in the development of quantum mechanics. Hydrogen gas was first artificially produced in the early 16th century by the reaction of acids on metals. In 1766–81, Henry Cavendish was the first to recognize that hydrogen gas was a discrete substance, and that it produces water when burned, the property for which it was later named. In Greek, hydrogen means water former. Industrial production is mainly from steam reforming natural gas, and less often from more energy-intensive methods such as the electrolysis of water. Most hydrogen is used near the site of its production, the two largest uses being fossil fuel processing, e.g., hydrocracking, and ammonia production, mostly for the fertilizer market. Hydrogen is a concern in metallurgy as it can embrittle many metals, complicating the design of pipelines and storage tanks. Properties. Combustion. Hydrogen gas, dihydrogen or molecular hydrogen, is highly flammable and will burn in air at a very wide range of concentrations between 4% and 75% by volume. Hydrogen gas forms explosive mixtures with air in concentrations from 474% and with chlorine at 595%. The explosive reactions may be triggered by spark, heat, or sunlight. The hydrogen autoignition temperature, the temperature of spontaneous ignition in air, is 500 degrees Celsius, 932 degrees Fahrenheit. Pure hydrogen-oxygen flames emit ultraviolet light and with high oxygen mix are nearly invisible to the naked eye, as illustrated by the faint plume of the Space Shuttle main engine, compared to the highly visible plume of a Space Shuttle solid rocket booster, which uses an ammonium perchlorate composite. The detection of a burning hydrogen leak may require a flame detector. Such leaks can be very dangerous. Hydrogen flames in other conditions are blue, resembling blue natural gas flames. The destruction of the Hindenburg airship was a notorious example of hydrogen combustion and the cause is still debated. The visible orange flames in that incident were the result of a rich mixture of hydrogen to oxygen combined with carbon compounds from the airship skin. H2 reacts with every oxidizing element. Hydrogen can react spontaneously and violently at room temperature with chlorine and fluorine to form the corresponding hydrogen halides, hydrogen chloride, and hydrogen fluoride, which are also potentially dangerous acids. Electron energy levels. The ground state energy level of the electron in a hydrogen atom is 13.6 eV, which is equivalent to an ultraviolet photon of roughly 91 nm wavelength. The energy levels of hydrogen can be calculated fairly accurately using the Bohr model of the atom, which conceptualizes the electron as orbiting the proton in analogy to the Earth's orbit of the Sunday. However, the atomic electron and proton are held together by electromagnetic force, while planets and celestial objects are held by gravity. Because of the discretization of angular momentum postulated in early quantum mechanics by Bohr, the electron in the Bohr model can only occupy certain allowed distances from the proton, and therefore only certain allowed energies. A more accurate description of the hydrogen atom comes from a purely quantum mechanical treatment that uses the Schrödinger equation, Dirac equation, or even the Feynman path integral formulation to calculate the probability density of the electron around the proton. The most complicated treatments allow for the small effects of special relativity and vacuum polarization. In the quantum mechanical treatment, the electron in a ground-state hydrogen atom has no angular momentum at all, illustrating how the planetary orbit differs from electron motion. Elemental molecular forms. There exist two different spin isomers of hydrogen diatomic molecules that differ by the relative spin of their nuclei. In the orthohydrogen form, the spins of the two protons are parallel and form a triplet state with a molecular spin quantum number of 1, 1 2 plus 1 2. In the parahydrogen form, the spins are antiparallel and form a singlet with a molecular spin quantum number of 0, 1 2 1 2. At standard temperature and pressure, hydrogen gas contains about 25% of the para form and 75% of the ortho form, also known as the normal form. The equilibrium ratio of orthohydrogen to parahydrogen depends on temperature, but because the ortho form is an excited state and has a higher energy than the para form, it is unstable and cannot be purified. At very low temperatures, the equilibrium state is composed almost exclusively of the para form. The liquid and gas phase thermal properties of pure parahydrogen differ significantly from those of the normal form because of differences in rotational heat capacities, as discussed more fully in spin isomers of hydrogen. The ortho/para distinction also occurs in other hydrogen-containing molecules or functional groups, such as water and methylene, but is of little significance for their thermal properties. The uncatalyzed interconversion between para and ortho H2 increases with increasing temperature, thus rapidly condensed H2 contains large quantities of the high-energy ortho form that converts to the para form very slowly. The ortho/para ratio in condensed H2 is an important consideration in the preparation and storage of liquid hydrogen. The conversion from ortho to para is exothermic and produces enough heat to evaporate some of the hydrogen liquid, leading to loss of liquefied material. Catalysts for the ortho-para interconversion, such as ferric oxide, activated carbon, platinized asbestos, rare earth metals, uranium compounds, chromic oxide, or some nickel compounds, are used during hydrogen cooling. Phases: gaseous hydrogen, liquid hydrogen, slush hydrogen, solid hydrogen, metallic hydrogen, covalent and organic compounds. While H2 is not very reactive under standard conditions, it does form compounds with most elements. Hydrogen can form compounds with elements that are more electronegative, such as halogens, e.g., F, Cl, Br, I, or oxygen. In these compounds, hydrogen takes on a partial positive charge. When bonded to fluorine, oxygen, or nitrogen, hydrogen can participate in a form of medium-strength non-covalent bonding with the hydrogen of other similar molecules, a phenomenon called hydrogen bonding that is critical to the stability of many biological molecules. Hydrogen also forms compounds with less electronegative elements, such as metals and metalloids, where it takes on a partial negative charge. These compounds are often known as hydrides. Hydrogen forms a vast array of compounds with carbon called the hydrocarbons, and an even vaster array with heteroatoms that, because of their general association with living things, are called organic compounds. The study of their properties is known as organic chemistry, and their study in the context of living organisms is known as biochemistry. By some definitions, organic compounds are only required to contain carbon. However, most of them also contain hydrogen, and because it is the carbon-hydrogen bond which gives this class of compounds most of its particular chemical characteristics, carbon-hydrogen bonds are required in some definitions of the word organic in chemistry. Millions of hydrocarbons are known, and they are usually formed by complicated synthetic pathways that seldom involve elementary hydrogen. Hydrides. Compounds of hydrogen are often called hydrides, a term that is used fairly loosely. The term hydride suggests that the H atom has acquired a negative or anionic character, denoted H, and is used when hydrogen forms a compound with a more electropositive element. The existence of the hydride anion, suggested by Gilbert and Lewis in 1916 for group 1 and 2 salt-like hydrides, was demonstrated by Moers in 1920 by the electrolysis of molten lithium hydride, LiH, producing a stoichiometry quantity of hydrogen at the anode. For hydrides other than group 1 and 2 metals, the term is quite misleading, considering the low electronegativity of hydrogen. An exception in group 2 hydrides is Bet2, which is polymeric. In lithium-aluminium hydride, the LH4 anion carries hydridic centers firmly attached to the Al3. Although hydrides can be formed with almost all main group elements, the number and combination of possible compounds varies widely. For example, more than 100 binary borane hydrides are known, but only one binary aluminium hydride. Binary indium hydride has not yet been identified, although larger complexes exist. In inorganic chemistry, hydrides can also serve as bridging ligands that link two metal centers in a coordination complex. This function is particularly common in group 13 elements, especially in boranes, boron hydrides, and aluminium complexes, as well as in clustered carborons. Protons and acids. Oxidation of hydrogen removes its electron and gives H+, which contains no electrons and a nucleus which is usually composed of one proton. That is why H+ is often called a proton. This species is central to discussion of acids. Under the Brønsted-Lowry theory, acids are proton donors, while bases are proton acceptors. A bare proton, H+, cannot exist in solution or in ionic crystals because of its unstoppable attraction to other atoms or molecules with electrons. Except at the high temperatures associated with plasmas, such protons cannot be removed from the electron clouds of atoms and molecules, and will remain attached to them. However, the term proton is sometimes used loosely and metaphorically to refer to positively charged or cationic hydrogen attached to other species in this fashion, and as such is denoted H+, without any implication that any single protons exist freely as a species. To avoid the implication of the naked solvated proton in solution, acidic aqueous solutions are sometimes considered to contain a less unlikely fictitious species, termed the hydronium ion, H3O+. However, even in this case, such solvated hydrogen cations are more realistically conceived as being organized into clusters that form species closer to H9O+. 4 other oxonium ions are found when water is in acidic solution with other solvents. Although exotic on Earth, one of the most common ions in the universe is the H+3 ion, known as protonate molecular hydrogen or the trihydrogen cation. Isotopes. Hydrogen has 3 naturally occurring isotopes, denoted 1 H, 2 H and 3 H other, highly unstable nuclei, 4 H to 7 H, have been synthesized in the laboratory but not observed in nature. 1. H is the most common hydrogen isotope with an abundance of more than 99.98%. Because the nucleus of this isotope consists of only a single proton, it is given the descriptive but rarely used formal name protium. 2. H, the other stable hydrogen isotope, is known as deuterium and contains one proton and one neutron in the nucleus. All deuterium in the universe is thought to have been produced at the time of the Big Bang, and has endured since that time. Deuterium is not radioactive, and does not represent a significant toxicity hazard. Water enriched in molecules that include deuterium instead of normal hydrogen is called heavy water. Deuterium and its compounds are used as a non-radioactive label in chemical experiments and in solvents for 1. HNMR spectroscopy. Heavy water is used as a neutron moderator and coolant for nuclear reactors. Deuterium is also a potential fuel for commercial nuclear fusion. 3. H is known as tritium and contains one proton and two neutrons in its nucleus. It is radioactive, decaying into helium-3 through beta decay with a half-life of 12.32 years. It is so radioactive that it can be used in luminous paint, making it useful in such things as watches. The glass prevents the small amount of radiation from getting out. Small amounts of tritium are produced naturally by the interaction of cosmic rays with atmospheric gases. Tritium has also been released during nuclear weapons tests. It is used in nuclear fusion reactions, as a tracer in isotope geochemistry, and in specialized self-powered lighting devices. Tritium has also been used in chemical and biological labeling experiments as a radiolabel. Hydrogen is the only element that has different names for its isotopes in common use today. During the early study of radioactivity, various heavy radioactive isotopes were given their own names, but such names are no longer used, except for deuterium and tritium. The symbols D and T, instead of 2, H and 3, H, are sometimes used for deuterium and tritium, but the corresponding symbol for protium, P, is already in use for phosphorus and thus is not available for protium. In its nomenclatural guidelines, the International Union of Pure and Applied Chemistry, IUPAC, allows any of D, T, 2, H, and 3, H to be used, although 2, H and 3, H are preferred. The exotic atom muonium, symbol mu, composed of an antimuon and an electron, is also sometimes considered as a light radioisotope of hydrogen, due to the mass difference between the antimuon and the electron. Muonium was discovered in 1960. During the muon's 2.2s lifetime, muonium can enter into compounds such as muonium chloride, MuCl, or sodium muonide, Na-mu, analogous to hydrogen chloride and sodium hydride respectively. History, discovery and use. In 1671, Robert Boyle discovered and described the reaction between iron filings and dilute acids, which results in the production of hydrogen gas. In 1766, Henry Cavendish was the first to recognize hydrogen gas as a discrete substance, by naming the gas from a metal-acid reaction in flammable air. He speculated that inflammable air was in fact identical to the hypothetical substance called phlogiston, and further finding in 1781 that the gas produces water when burned. He is usually given credit for the discovery of hydrogen as an element. In 1783, Antoine Lavoisier gave the element the name hydrogen, from the Greek delta rho omicron hydro meaning water and gamma epsilon nu genes meaning creator, when he and Laplace reproduced Cavendish's finding that water is produced when hydrogen is burned. Lavoisier produced hydrogen for his experiments on mass conservation by reacting a flux of steam with metallic iron through an incandescent iron tube heated in a fire. Many metals such as zirconium undergo a similar reaction with water, leading to the production of hydrogen. Hydrogen was liquefied for the first time by James Dewar in 1898 by using regenerative cooling and his invention, the vacuum flask. He produced solid hydrogen the next year. Deuterium was discovered in December 1931 by Harold Urey, and tritium was prepared in 1934 by Ernest Rutherford, Mark Oliphant, and Paul Hartek. Heavy water, which consists of deuterium in the place of regular hydrogen, was discovered by Urey's group in 1932. François-Isaac de Rivaz built the first de Rivaz engine, an internal combustion engine powered by a mixture of hydrogen and oxygen, in 1806. Edward Daniel Clark invented the hydrogen gas blowpipe in 1819. The Dobereiner's lamp and limelight were invented in 1823. The first hydrogen-filled balloon was invented by Jacques Charles in 1783. Hydrogen provided the lift for the first reliable form of air travel following the 1852 invention of the first hydrogen-lifted airship by Henri Giffard. German Count Ferdinand von Zeppelin promoted the idea of rigid airships lifted by hydrogen that later were called Zeppelins, the first of which had its maiden flight in 1900. Regularly scheduled flights started in 1910, and by the outbreak of World War I in August 1914, they had carried 35,000 passengers without a serious incident. Hydrogen-lifted airships were used as observation platforms and bombers during the war. The first non-stop transatlantic crossing was made by the British airship R-34 in 1919. Regular passenger service resumed in the 1920s, and the discovery of helium reserves in the United States promised increased safety, but the U.S. government refused to sell the gas for this purpose. Therefore, H-2 was used in the Hindenburg airship, which was destroyed in a mid-air fire over New Jersey on May 6, 1937. The incident was broadcast live on radio and filmed. Ignition of leaking hydrogen is widely assumed to be the cause, but later investigations pointed to the ignition of the aluminized fabric coating by static electricity. But the damage to hydrogen's reputation as a lifting gas was already done, and commercial hydrogen airship travel ceased. Hydrogen is still used, in preference to non-flammable but more expensive helium, as a lifting gas for weather balloons. In the same year, the first hydrogen-cooled turbogenerator went into service with gaseous hydrogen as a coolant in the rotor and the stator in 1937 at Dayton, Ohio, by the Dayton Power and Light Co. Because of the thermal conductivity of hydrogen gas, this is the most common type in its field today. The nickel hydrogen battery was used for the first time in 1977 aboard the U.S. Navy's Navigation Technology Satellite 2, NTS-2. For example, the ISS, Mars Odyssey, and the Mars Global Surveyor are equipped with nickel hydrogen batteries. In the dark part of its orbit, the Hubble Space Telescope is also powered by nickel hydrogen batteries, which were finally replaced in May 2009, more than 19 years after launch and 13 years beyond their design life. Role in quantum theory. Because of its simple atomic structure, consisting only of a proton and an electron, the hydrogen atom, together with the spectrum of light produced from it or absorbed by it, has been central to the development of the theory of atomic structure. Furthermore, study of the corresponding simplicity of the hydrogen molecule and the corresponding cation H+. 2. Broad understanding of the nature of the chemical bond, which followed shortly after the quantum mechanical treatment of the hydrogen atom had been developed in the mid-1920s. One of the first quantum effects to be explicitly noticed, but not understood at the time, was a Maxwell observation involving hydrogen, half a century before full quantum mechanical theory arrived. Maxwell observed that the specific heat capacity of H2 unaccountably departs from that of a diatomic gas below room temperature and begins to increasingly resemble that of a monatomic gas at cryogenic temperatures. According to quantum theory, this behavior arises from the spacing of the quantized rotational energy levels, which are particularly wide-spaced in H2 because of its low mass. These widely spaced levels inhibit equal partition of heat energy into rotational motion in hydrogen at low temperatures. Diatomic gases composed of heavier atoms do not have such widely spaced levels and do not exhibit the same effect. Antihydrogen H is the antimatter counterpart to hydrogen. It consists of an antiproton with a positron. Antihydrogen is the only type of antimatter atom to have been produced as of 2015. Natural occurrence. Hydrogen, as atomic H, is the most abundant chemical element in the universe, making up 75% of normal matter by mass and more than 90% by number of atoms. Most of the mass of the universe, however, is not in the form of chemical element type matter, but rather is postulated to occur as yet undetected forms of mass such as dark matter and dark energy. This element is found in great abundance in stars and gas giant planets. Molecular clouds of H2 are associated with star formation. Hydrogen plays a vital role in powering stars through the proton-proton reaction and the CNO cycle nuclear fusion. Throughout the universe, hydrogen is mostly found in the atomic and plasma states, with properties quite different from those of molecular hydrogen. As a plasma, hydrogen's electron and proton are not bound together, resulting in very high electrical conductivity and high emissivity, producing the light from the Sun and other stars. The charged particles are highly influenced by magnetic and electric fields. For example, in the solar wind they interact with the Earth's magnetosphere, giving rise to Birkeland currents and the aurora. Hydrogen is found in the neutral atomic state in the interstellar medium. The large amount of neutral hydrogen found in the damped Lyman alpha systems is thought to dominate the cosmological baryonic density of the universe up to redshift Z equals 4. Under ordinary conditions on Earth, elemental hydrogen exists as the diatomic gas, H2. However, hydrogen gas is very rare in the Earth's atmosphere, 1 ppm by volume, because of its light weight, which enables it to escape from Earth's gravity more easily than heavier gases. However, hydrogen is the third most abundant element on the Earth's surface, mostly in the form of chemical compounds such as hydrocarbons and water. Hydrogen gas is produced by some bacteria and algae and is a natural component of flatus, as is methane, itself a hydrogen source of increasing importance. A molecular form called protonate molecular hydrogen, H+, 3, is found in the interstellar medium, where it is generated by ionization of molecular hydrogen from cosmic rays. This charged ion has also been observed in the upper atmosphere of the planet Jupiter. The ion is relatively stable in the environment of outer space due to the low temperature and density. H+, 3 is one of the most abundant ions in the universe, and it plays a notable role in the chemistry of the interstellar medium. Neutral triatomic hydrogen H3 can exist only in an excited form and is unstable. By contrast, the positive hydrogen molecular ion, H+, 2, is a rare molecule in the universe. Production. H. 2 is produced in chemistry and biology laboratories, often as a byproduct of other reactions, in industry for the hydrogenation of unsaturated substrates, and in nature as a means of expelling reducing equivalents in biochemical reactions. Steam reforming. Hydrogen can be prepared in several different ways, but economically the most important processes involve removal of hydrogen from hydrocarbons, as about 95% of hydrogen production came from steam reforming around year 2000. Commercial bulk hydrogen is usually produced by the steam reforming of natural gas. At high temperatures, 1400 K, 1100 degrees C or 2000 degree F, steam, water vapor, reacts with methane to yield carbon monoxide and H2 CH 4 plus H 2O plus 3H2. This reaction is favored at low pressures but is nonetheless conducted at high pressures, 2.0 MPa, 20 atm, or 600 in Hg. This is because high pressure H2 is the most marketable product and pressure swing adsorption, PSA, purification systems work better at higher pressures. The product mixture is known as synthesis gas because it is often used directly for the production of methanol and related compounds. Hydrocarbons other than methane can be used to produce synthesis gas with varying product ratios. One of the many complications to this highly optimized technology is the formation of coke or carbon. CH 4C plus 2H2. Consequently, steam reforming typically employs an excess of H2O. Additional hydrogen can be recovered from the steam by use of carbon monoxide through the water-gas shift reaction, especially with an iron oxide catalyst. This reaction is also a common industrial source of carbon dioxide. CO and H2O. 2 plus H2. Other important methods for H2 production include partial oxidation of hydrocarbons, 2CH 4 plus O, 2CO plus 4H2, and the Cole reaction, which can serve as a prelude to the shift reaction above. C and H2O and H2. Hydrogen is sometimes produced and consumed in the same industrial process, without being separated. In the Haber process for the production of ammonia, hydrogen is generated from natural gas. Electrolysis of brine to yield chlorine also produces hydrogen as a CO product. Metal acid. In the laboratory, H2 is usually prepared by the reaction of dilute non-oxidizing acids on some reactive metals such as zinc with Kipps apparatus. Zn plus 2H plus Zn2 plus H2. Aluminium can also produce H2 upon treatment with bases. 2Al plus 6H 2O plus 2O 2Al, O 4 plus 3H 2. The electrolysis of water is a simple method of producing hydrogen. A low-voltage current is run through the water, and gaseous oxygen forms at the anode while gaseous hydrogen forms at the cathode. Typically the cathode is made from platinum or another inert metal when producing hydrogen for storage. If, however, the gas is to be burnt on site, oxygen is desirable to assist the combustion, and so both electrodes would be made from inert metals. Iron, for instance, would oxidize, and thus decrease the amount of oxygen given off. The theoretical maximum efficiency, electricity used versus energetic value of hydrogen produced, is in the range 80–94%. 2H 2O, L, 2H 2, G, plus O 2, G. An alloy of aluminium and gallium in pellet form added to water can be used to generate hydrogen. The process also produces alumina, but the expensive gallium, which prevents the formation of an oxide skin on the pellets, can be reused. This has important potential implications for a hydrogen economy, as hydrogen can be produced on-site and does not need to be transported. Thermochemical. There are more than 200 thermochemical cycles which can be used for water splitting, around a dozen of these cycles such as the iron oxide cycle, cerium, 4, oxide cerium, 3, oxide cycle, zinc-zinc oxide cycle, sulfur-iodine cycle, copper-chlorine cycle, and hybrid-sulfur cycle are under research and in testing phase to produce hydrogen and oxygen from water and heat without using electricity. A number of laboratories, including in France, Germany, Greece, Japan, and the USA, are developing thermochemical methods to produce hydrogen from solar energy and water. Anaerobic corrosion. Under anaerobic conditions, iron and steel alloys are slowly oxidized by the protons of water concomitantly reduced in molecular hydrogen, H. 2. The anaerobic corrosion of iron leads first to the formation of ferrous hydroxide, green rust, and can be described by the following reaction. Fe plus 2H. 2O Fe, O. 2 plus H. 2. In its turn, under anaerobic conditions, the ferrous hydroxide, Fe, O. 2, can be oxidized by the protons of water to form magnetite and molecular hydrogen. This process is described by the Schicker reaction. 3 Fe, O. 2 Fe. 3O. 4 plus 2H. 2O plus H. 2. Ferrous hydroxide magnetite and water and hydrogen. The well-crystallized magnetite, Fe. 3O. 4, is thermodynamically more stable than the ferrous hydroxide, Fe. O. 2. This process occurs during the anaerobic corrosion of iron and steel in oxygen-free groundwater and in reducing soils below the water table. Geological occurrence, the serpentinization reaction. In the absence of atmospheric oxygen, O2, in deep geological conditions prevailing far away from Earth atmosphere, hydrogen, H2, is produced during the process of serpentinization by the anaerobic oxidation by the water protons, H+, of the ferrous, Fe2+, silicate present in the crystal lattice of the phyolite, Fe. 2SiO. 4. The olivine iron end member. The corresponding reaction leading to the formation of magnetite, Fe. 3O. 4, quartz, SiO. 2, and hydrogen, H. 2, is the following. 3 Fe. 2 SiO. 4 plus 2H. 2O2 Fe. 3O. 4 plus 3 SiO. 2 plus 3H. 2. Phyolite and water magnetite and quartz and hydrogen. This reaction closely resembles the Schicker reaction observed in the anaerobic oxidation of the ferrous hydroxide in contact with water. Formation in transformers. From all the fault gases formed in power transformers, hydrogen is the most common and is generated under most fault conditions. Thus, formation of hydrogen is an early indication of serious problems in the transformer's life cycle. Applications. Consumption in processes. Large quantities of H2 are needed in the petroleum and chemical industries. The largest application of H2 is for the processing, upgrading, of fossil fuels, and in the production of ammonia. The key consumers of H2 in the petrochemical plant include hydrodealkylation, hydrodesulfurization, and hydrocracking.
Please subscribe and thanks for watching.